going to talk to you about this. We're going to redraw or revisit the last carbocation that we had. So when we did E2 reactions, our strategy was to find alpha, expand all unique beta positions, right? And then at each beta position, check geometry. We wanted 180 or 0, anti or syn periplanar, and then finally do E2 reactions. This is just the general logical steps when we have an E2. We have a substrate, we have a base, we find its alpha position, that's where the leaving group is, we find all the beta positions, we expand them, we check geometry, and we do the E2. For kind of like linear alkyl halides, this 180-0 is not even really an issue because we have free rotation. This really becomes an issue when we have chairs. So it wasn't universal that we had to do this every time. In fact, when we have a problem like this, no need to draw Newman projections unless I ask you to. You know that beta hydrogens here, they'll react no problem. There are geometry requirements for the E1 reaction, but we don't have to think about them. We're not going to explore them in the same depth that we did yesterday. I want to actually look at one picture here of this last carbocation we had. I want to take this tertiary butyl carbocation, and I want to look at just one small detail about how the elimination reaction takes place at the beta position. So I'm going to call this alpha, call this beta. There's 3 beta positions, they're all identical. I'm going to expand at beta. We did this on the last page we were working on. I'm just going to take one of these beta groups. I'm going to expand it. By expanding it, it allows us to see all of the bonds. So when we do a mechanism, you can easily draw an arrow to the acidic proton, move these here, you can see where bonds are forming. So that's why we expand this to some extent. These are beta and alpha. And the way this reaction actually works, there is some geometric requirement, but we're not going to have to focus or study it too much. What I'm going to do now is I'm going to redraw this carbocation. I want you to redraw it as well. I want to draw it with an empty p orbital. And I'm going to draw this kind of in a semi-sawhorse, weird sort of fashion, and I'm going to give you time to catch up. And I'm going to explain why I'm drawing it this way. But I'd like you to draw this in a semi-sawhorse fashion. The sawhorse portion is kind of illustrated here. Looks a little bit like the sawhorses we were working with yesterday, where we have bromine down or bromine up. We could actually draw this as a Newman projection. We could think about that. We're not going to. But this is our carbocation. It's sp2 hybridized, and we have an empty p orbital right here. And I've just drawn that. And it turns out that these electrons here have to line up with this empty p orbital. They have to be syn periplanar or anti-periplanar, doesn't matter, but they kind of have to line up like this. But for this molecule, this is flat right here. This is sp2, so this atom, this atom, this atom, and this carbon are all flat. But this freely rotates, so the hydrogens here can rotate all around, and you can easily imagine that these can line up perfectly for one another. And so when this happens and we have sulfate or water, let's just draw sulfate here. Drawing it really small, it's not really the most important thing. But what happens for this reaction to work is this proton's acidic. It's acidic because these electrons in this bond are being pulled by induction to this carbocation. And as we pull off this with a weak base, any base works, these electrons literally fall into this p orbital. They literally fall into this p orbital. And this stays sp2 hybridized as it forms an alkene, and this carbon becomes sp2 hybridized, and then we finally get to an alkene. I'm just going to draw the alkene kind of small here just to finish this off. Okay, what is the alkene that we make? This double bond that's forming here is right here. These are the two methyl groups. There's two hydrogens left. But this is the geometric requirement for an E1 reaction to take place, that these two things have to line up. But for us, honestly, it's not going to be important for us. It's always going to be able to rotate freely. We're always going to be able to get to a conformation. So you'll never have to draw anything like this. You can always stick to these flat diagrams. You can always stick to this diagram here is always going to be sufficient for us to draw the mechanism. Expand at the beta position. Just have base come in, pluck off this proton. These electrons go here, and you can easily draw this product. I'm just putting this here for your edification. It's important for us that we just have this inner note somewhere, that we have some understanding of it. And there is a geometric requirement for this E1 reaction to take place. It requires that this empty orbital and this full orbital line up in space. And it's similar to E2. In the E2 case, we'd have a leaving group here. So we'd have bromine where my finger is. And we need these 180 degrees apart from one another. And as base comes in and pulls off this acidic proton, these electrons fall into an antibonding orbital, which causes this to break and a new bond to form. That's kind of a high-level discussion. It's okay if you don't follow perfectly what I just said there. Here, this picture is crystal clear, though. The E1's really nice to understand from a molecular orbital picture why these things have to line up like this. These electrons have to line up with here, because if this bond breaks, we're going to have a cloud of electrons here temporarily in an sp3 orbital, and we're going to have a negative charge plus charge. It's going to immediately zoom and overlap with an empty orbital to form a bond. And if these are at the wrong angle, then we can't have overlap between these two orbitals. Just like forming a sigma bond, it comes together in a collinear fashion this way. Can't really come together this way or this way. Mathematically, it doesn't work, and the orbitals don't mix. With pi bonds, we bring two p lobes together sideways. Can't bring them together like this or like this or like this. They have to come perfectly together like this. And so as we're forming this pi bond, there is some constraint here too on geometry. The p orbital and the pair of electrons have to kind of come in together. They don't work at 60, 90, 45. They really only come together periplanar in the same plane. But again, for these molecules, we always have free rotation. We always can get to this conformation. We don't have to draw this conformation, but this is the reason behind why. Let's move on and try a more useful example, a more practical example, where we get to explore and put everything together. This will use some of our information from yesterday and our skills with finding alpha and beta and unique positions. And the one that I have in mind, I want to take methyl cyclohexanol. So I guess this is 1-methyl cyclohexanol. And we're always going to do these reactions in the presence of sulfuric acid. It's a small token gift from me to you for your hard work in this class. We're not going to explore this in other contexts. Sulfuric acid does have this ability to remove water from things. It's a very special type of acid. It's one you never ever want to get in your eyes in a laboratory. It's why you always want your entire lives to wear goggles in laboratories wherever acid's particularly involved. This can actually suck, just one drop of concentrated sulfuric acid will suck all the water out of your eye, and any OH groups will be immediately eliminated. It's not really what your eye wants to do or wants to go through on a Monday morning in laboratory. So please just wear your goggles. But this is a very powerful type of acid. It's dehydrating, meaning it removes water from things. And it's not just like sucking water out of like like removing water from the air like a dehumidifier. It's breaking covalent bonds as it does this and leaving behind things that your eyes definitely don't want to have happen. But in synthetic mechanisms to make molecules from other molecules, or in biological processes at the microscopic or atomic level, these types of elimination reactions take place to carry out specific biological function. So that's why we're going to practice these things. And we have an acid-base reaction that happens first. This is the acid. This is the base. It's an equilibrium process. We're going to draw all these steps. This is how we actually explain the E1 reaction taking place. There's lots of steps involved, but they're not necessarily difficult if you've been following along and alive in this class. we've made a bad leaving group a good leaving group. Is also equilibrium process. And finally we get to a tertiary carbocation, which we would predict from our starting alcohol. To work through and correctly, with some fidelity, predict and explain all the major products for this reaction, we now look at this and identify things as alpha, beta, beta. We're going to call this beta 1. We're going to call this beta 2. There's no reason to call this beta 3. This position is beta 1 by symmetry. By any possible metric in the world, this is the exact same thing. So if you want to do it, go for it, but you're just going to be wasting time. So again, this is unique. This is unique. We would expect these lead to different products. So we'll explore them one at a time. What I mean by that is, let's expand at beta, let's do beta 2 first, okay? This is the same technique we've been using for E2 reactions. With the E2 reaction, alpha was described as where there was a leaving group. This is the same technique, alpha and beta, we were using with carbocation rearrangements in SN1 chemistry. We see a carbocation, we can start labeling it right away in the E1 reaction. So what I mean by expanding at the beta 2 position, I'm going to draw the cyclohexane ring just slightly, well, same way, but I'm just going to rotate this carbon off to the right side here. So this is our beta 2 position expanded. We can use a lot of conjugate bases to do this. This thing that we actually use isn't really that important. Some textbooks will use water. Some textbooks will use CB for conjugate base. But for us, let's just use the conjugate base of the acid we used. If you use something else on your exams, I'll know what to do. If you use sodium hydroxide, you will not get points for it because this reaction does not have a hydroxide in it, but it has lots of weak bases in it. This is a conjugate base. It has water in it that just left. So there's enough reagents here for you to pick from. If you really just need some direction, you want me to tell you what to do, use sulfates. These two things can line up perfectly because there's free rotation here. We don't need to draw it or think any more about it. But if we do the mechanism, these protons are rendered acidic because there's a carbocation nearby. And we want to stabilize this. One way to stabilize it is by giving it electrons. And here we've made a di-substituted. Double bond. Okay? Some of you probably have already anticipated what the other product should look like. And maybe some of you are thinking whether we need to draw chairs or not. I'm going to show you that we don't need to draw chairs. But let's now do the expansion at the beta 1 position. So we're going to expand at the beta 1 position to explain and find other new products. Again, what I mean by that is quite simple. This is the beta 1 position. I've just drawn these two hydrogens. This molecule has a sp2 carbon in it. It's no longer a chair. Chair conformation is cyclohexane, where we have sp3, 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 sp3. We no longer have that. So this molecule is no longer chair-shaped. We can't even really draw it as a chair. Indeed, I'm going to just highlight a few atoms here. I'll put them in a red pen. Let's put a little circle around this. This one, this one, this one, and this one are now all flat and in the same plane because this is sp2 hybridized. sp2 hybridized carbon is flat, trigonal planar. These are 120-degree bond angles. This is going to come back a little bit later. sp2 carbon, trigonal, planar. Trigonal is 120 degrees. Planar means flat. So this sequence here is flat. It's no longer bent like that chair is bent. It's not up, down, up, down. This is perfectly flat molecule. And either one of these hydrogens is going to be able to line up perfectly. Imagine a p orbital just coming out of the paper towards us. Kind of from the last page we were working on, I drew a p orbital, we showed the hydrogen lining up with it. This hydrogen can easily line up with it. So can this one, because this whole molecule here is flat now. Okay, so we don't need to draw chairs. It's impossible to actually draw a chair for this anymore. It's not a chair. We can draw a three-dimensional picture of it, for sure, but this is not a chair. And so, point of all this is, we don't need to draw it in a chair. It's not a chair. This hydrogen will overlap with the empty p orbital, and this will give rise to a tri-substituted product, which maybe some of you had already anticipated early on looking at this problem. Following Zaitsev's rule from yesterday, this would be our major product. If we were asked to predict it, this would be our minor. When we run this reaction in reality, we get about 80% yield of this one and about 20% yield of this one, roughly. Those numbers, you have to actually do an experiment